To begin our conversation around the domain of functions, I thought it would be a good idea to look at a variety of different types of graphs and get a sense of what domain would look like in each one of those situations. So you can see down the left-hand side, I have a variety of different types of equations that we might want to look at. No one is expecting you to know how to graph all of these. You should have some idea of how to graph the absolute value. You should have some idea of how to graph a linear function. You might have some experience with some quadratics, maybe some square roots, but these two at the bottom are probably a little less familiar to you, and that's okay. The purpose of this exercise is not to master all of this graphing. That's what's going to happen throughout the remainder of this course. The purpose of this exercise is to look at the shapes of these graphs and how they're determined by the domains that are allowed. So we're going to begin first with the easiest one, which is the one right at the top. This is what we call a linear function. And when we graph a linear function, and you can take a look at the picture here, we get this nice straight line that is theoretically going to continue on in every direction. If I zoom out a little bit, you'll see that that line keeps going and going and going. It should be fairly obvious at this point that I am able to take any x value I want and substitute it into that equation. And that is something that we should anticipate continuing for every linear equation. Every number that exists in the real numbers could be multiplied by 5 and have 3 taken away from it. Because of that, this first graph has a domain of all the real numbers. Our second type is another type that you're probably familiar with from our last lesson. This is our absolute value functions. Reviewing that material from the last section, we'll notice that we have a -3 in here, which is a transition to the right. We have a -6, or a translation to the right. We have a -6 here, which is a translation down. And then we have this 3 out front that's doing the slope change for us, allowing us to have steeper sides of the V, and we get this look. So we went 3 right and 6 down, and we get the steeper sides of the V. If I zoom out, I see that this graph continues on forever in both directions, pointing up. We'll have some things to talk about as it pertains to the range of this graph, but for the domain, same as the linear. I can substitute any number I want in for the x. I can subtract 3, I can multiply by 3, and then I can subtract 6. I can follow the order of operations on this absolute value function, and every possible x value will give me an answer, or give me a domain, or excuse me, a range output. We'll get a range output for every one of those potential inputs. This next type I mentioned earlier is one that you might be a little bit familiar with based on some previous experiences, but this is what we call a quadratic. We have this dominant x squared term in the front that's going to give us our classic parabola rounded off look. Very similar to the absolute value. A lot of people like to say that this one looks like a U while the absolute value looks like a V. But in this U shape, you get the exact same scenario. There's nothing stopping us from taking any value of x, substituting it into x squared, substituting it into where that x is, and getting an output value. You'll notice as x gets larger in either direction, so larger absolute value to the left, larger to the right, as x gets larger, we get these outputs that are much, much higher. We're all the way over here at 22 195s or so. So you get significantly large amounts pretty quickly for this very simple quadratic, but that doesn't mean that we can't put any number in we want. We could put in smaller numbers like 0. We could put in 2. There's one at 6. There's one at -2. So we have outputs all over the place, different types of numbers that we can put in as domain/input values. Our next example is what's called a radical or a square root function. This one is a little bit trickier. Instead of it being limited in terms of the bottom of it, in the absolute value and in the quadratic, we saw nothing below a certain point. This one is actually going to be limited slightly differently. You'll see that it just sort of randomly starts out in space over here and then proceeds off to the right. If I zoom in on that location just a little bit, I see that that starting value is at -3, -1, which asks the question, what's happening there that does not allow this graph to continue any farther to the left? And that requires you to think a little bit about what's happening inside of here. Remember that when we take the square root, we want the number that we take the square root of to be positive. We cannot take the square root of a negative. If we cannot take the square root of a negative, we must guarantee the fact that this will come out positive. That doesn't, or excuse me, positive or zero. For this particular situation, that doesn't happen until this spot right here. If I try to go over to -4, and I imagine subbing -4 into this rule, -4 plus 3 is -1, the square root of -1 is nothing. There's just nothing happening over here. This graph starts at this spot right here and proceeds to the right because all of these potential domain values, all of these numbers, 1, 2, 3, 4, they all will work. They will all create a positive in here, where anything to the left of -3 does not. So for this one, while the first three were all domain real numbers, all real numbers, exactly what we would hope, this one's a little bit trickier in that it is x is greater than or equal to -3, which is a slightly different situation. We'll talk a little bit more in a later video about how to do that algebraically. All right, turning up the heat onto something that you probably are not familiar with at all, we are going to look quickly at what's called a rational function. A rational function is a function made up of a polynomial over another polynomial. Now, this is written in what's called its factored form. The numerator and the denominator are both factored. The numerator has a common factor of 9. The denominator was a trinomial factored as x plus 4 and x plus 2. It can be kind of shocking when you see this for the first time because these are all things that we're familiar with. This bottom is technically a quadratic. The top is technically linear. But when you mix the two of them together, we do get an admittedly strange look. Now, there's a couple things you need to notice about this. First is that as this graph comes in from the left and shoots downward, and as this graph comes in from the right and shoots upward, you do get a line right here that it does not cross. Now, if you're careful to detect that line, you'll see that that line is at x is equal to -4, and that's not an accident. Take a look at the denominator right here. X equals -4 has some relevance to that denominator for sure. And we'll talk a little bit more about that in a future video. You'll also see that if I'm to trace along this graph and look at all of these different points, that something strange happens when I get to -2. So as I scroll this way and I get to -2, it's flashing up there. It's a little hard to get it accurately. -2 is undefined. So while I get that line that it doesn't cross at -4, I also get this situation where there's all of these other points, but at -2, there's nothing. And if you look carefully at the function, you could probably detect why. Take a look at this denominator. X is equal to -2 is going to have something of relevance down there as well. So the rational functions are a little bit easier to detect because you get weird things and weird consequences based on what is in the denominator. The radical one was based on what's in the radicand versus these top three, which were all good. The last type that we're going to look at very quickly in graph form is an exponential. An exponential has a unique characteristic of always wanting to put out positive results. So similar to a square root always wanting to put out positive results, an exponential also likes to put out positive results. The difference between the exponential and the radical is the exponential will take on anybody and attempt to put out those positive results. But the careful observers among us will notice this +1 right here. That +1 has the added effect for this particular graph of moving the graph up 1 unit. So if we zoom in, we can see that instead of going down to 0, I get bottomed out at 1. And it looks like I just carry along that line. But the way that the exponential is structured, and because it always wants to stay above 0, if I zoom in and I keep zooming in, I'll see that if I'm able to zoom in with a certain level of accuracy, I'm not actually on that line. That's the 1 line right there. I'm actually right above it. And I can see that I stay above it. And before you think to yourself, well, if I scroll out far enough, and look how I'm getting closer. If I'm just getting closer and closer to that line, eventually I'm going to be right on top of it. That's true to a certain extent, but then you just zoom in some more. And you let the accuracy of the calculator do the work for you, and you see that you never touch that. Look how zoomed in we are, 0.995 is the next solid line we see, and I'm still not on top of that one line. So while there are weird little characteristics to some of these graphs, this one has a domain of all the real numbers, despite the fact that it has some limit to its range. So we can find ourselves in situations where we might think it's one thing. Oh, we have this limiting line right here where I'm not going to go past it. But that has no effect on the domain. All real numbers are allowed in this exponential function. In this one, it's more interesting to talk about the range, and we will do that in a future video. So again, this was not about memorizing all of these different types of graphs. That was not the intention of this exercise. Looking at these different types of graphs gives us an idea of what is and isn't allowed in each one of them, because they're not all the same. They're not going to just be all real numbers all the time. And depending upon where a graph is limited and what calculations you can and can't do will determine whether or not you are allowed to use particular inputs, particular numbers in the domain of a function.